Here in Lecture 3 of Differential Equations and Linear Algebra, I'm going to start doing what I think will be my typical practice to break the lecture up into two smaller parts, a Part A and a Part B. Part A will mostly be about differential equations and some difference equations too, like we've talked about. And Part B will mostly be about linear algebra. Though of course there's got to be some overlap between these subjects, otherwise why would we combine them into one course? So look for those overlaps. Over time, the overlaps will get more and more clear, especially in our main text here, Differential Equations by Blanchard, Devaney, and Hall. They'll be most explicit in Chapter 3. From my online textbook for linear algebra, Visual Linear Algebra Online, and my blog, infinityisreallybig.com, they will start to become more explicit in Chapter 2. That's my plan. All right, so Lecture 3A, this lecture, is about differential equations. I'm going to start by actually looking at the pendulum again, like we did in Lecture 2. Then we'll focus mostly on Newton's law of heating and cooling, mostly on the cooling part. More on separation of variables, which is a technique to solve differential equations. And we'll introduce the very important idea of a slope field. Then Lecture 3B, we do the linear algebra. The change of coordinates is related to the end of Lecture 2. And we looked at the visual relationship between rectangular coordinates and skew coordinates, where one axis was slanted. That'll be a little bit more explicit here. We'll look at actual equations to transform back and forth between those two coordinate systems. And then we'll introduce the very important idea of vectors. All right, but let's start with the pendulum. In Lecture 2 at the beginning, we looked at the unforced, undamped, nonlinear pendulum. A pendulum is a mass attached to a thin and essentially massless rod, even though that's not really realistic, swinging back and forth under the influence of gravity when you give it an initial angle and maybe let it go from rest. And that's what I did. In fact, I gave it an initial angle. Theta equals 0 is going to be pointing straight down. I went close to pi radians. In fact, I used 3 as my initial angle, 3 radians. And I let it go from rest, and we saw this kind of back and forth motion in Lecture 2 with the unforced, undamped, nonlinear pendulum. Undamped means no friction, so you imagine it going back and forth like this forever. When we graph the angle, theta, and the angular velocity, v, as functions of time, we saw oscillatory periodic behavior, but because the mass sort of spends a long time near the peak, it was not exactly pure sines and cosines. Okay? What about a forced pendulum? Well, let's look at the motion itself first, and let me just warn you, the motion in this PowerPoint is going to be very fast and very confusing, unrealistic looking. Don't worry about that. I am going to slow the motion down when we look at Mathematica here. So there it is, very fast. I couldn't get it to go slower in the PowerPoint. The key thing we want to get out of this is the relationship between the actual motion and this thing called the phase plane, where this point is moving around the phase plane and it tells you about the actual motion itself. The coordinates, here this is related to the end of Lecture 2, of this point as it moves around, this parametric curve, tell you the state of the system at any moment in time. It tells you the angle and it tells you the angular velocity at any moment in time. What's the differential equation? It's this. This is the differential equation. Here's your initial conditions. Second derivative of theta with respect to time is the angular acceleration. Radians per second squared. Not meters per second squared, radians per second squared. This part of the model is the same as the unforced undamped pendulum. Part of what goes into that second derivative is the opposite of the sign of the angular coordinate, where theta equals 0 is pointing straight down, theta is positive over here, theta is negative over there. This part, cosine of t, and yes, that is a t there, not a theta, that's time, is the external forcing. That's causing the motion to be so strange. The initial conditions are the same. Theta of 0 is 3, theta prime, or v of 0 is 0. What about a formula for the solution? Well, if the unforced solution, which was simpler, didn't have a formula, this one probably doesn't either. There's no simple formula for it. You could define a new function and give it a name, and that would be a new formula, so to speak. But we would, if nobody defined that function, we'd have to sort of just numerically approximate it, which is what's really going on here. Let's look at this more slowly by looking at the Mathematica. So So yeah, now we can see the motion more slowly, and sometimes it looks like somewhat ordinary oscillating, but sometimes it goes around the horn, for example, and that doesn't, and, it almost stalled there. What in the world's going on there? And what is the nature of this external forcing? What could be causing this? It could be lots of things. It could be the wind. It could be, maybe this is where the thin rod is hooked to some bar that's going into the wall, and maybe you grab that rod and swing it around and around like this. That would be the external forcing. Of course, you can't, I didn't put that in the visual. We're focused on just the mass on the thin rod itself. If I stop this at any moment in time, say right here. Well, let's go a little bit backwards here. Say right at time equals, say, 10.2. At that moment in time, what is the phase plane telling you about the motion? It's telling you both the angular coordinate, what is that angle, and what's the angular velocity. Notice that the coordinates of this point right here, not letting me right there, its first coordinate, its theta coordinate, is about a little bit bigger than the 5. This angle here, starting from 0 going downwards, is a little bit bigger than 5 radians. Maybe somewhere around 300 degrees. You might want to see if you can do that conversion. What about the second coordinate? That's this point right there. A little less than -2. Maybe -2.3 or something like that. I can't quite tell. That would be the angular velocity in radians per second. About -2.3. So what does that tell you? That's the rate of change of theta with respect to time, instantaneous at this moment in time. If I let time increase a tiny little bit, say from 10.2 to 10.3, 0.1 seconds, tenth of a second, I should expect the angle will change by approximately -2.3 times 0.1, about -0.23 radians, which is maybe like, I don't know, 10 or 20 degrees, something like that. Let's see if that happens. So I should see, if I change this 10.2 to a 10.3, the angle should be a little smaller. I haven't entered it yet. Watch it. Okay, you see where it is? I'm about to enter it here. The angle should be a little smaller. Yeah, it's a little smaller. About 10 to 20 degrees smaller. This point in the phase plane moved to the left a little bit. The angle got a little smaller. Okay? That's what you want to be able to do, is go back and forth between the actual motion and the phase plane. We're going to do this a lot in this class, or the whole semester, so if you don't quite get it right now, it's going to keep coming back. All right, let's get on to our main content for this lecture. Yes, there's no simple formula for the solution. The main content is looking at the heating and cooling, and also ultimately about slope fields. But I think we need to address this as well. Maybe you've wondered, why are the difference in differential equations that we've considered called linear? I've called them linear, when the models themselves are exponential. In other words, the solutions are exponential. A linear difference equation that we've looked at is of this form. Y sub n plus 1 equals k times y. The population, say, at time n plus 1 is k times the population at time n, where n is a whole number, 0, 1, 2, 3, etc. Why is that a linear difference equation? It's because I can think of k times yn as being f of yn, where f is a linear function of, call it y. F of y equals k times y. It's a linear function of y. That's why this equation is called linear. Okay, but its solutions, the model itself we saw in lecture 2, was exponential. We guessed the answer from lecture 2. Let me show you that you can do it without guessing as well. You can essentially integrate the equation, except I'm going to write it as yn equals k times yn minus 1 instead, because I'd like a direct formula for yn itself. I don't have to do this, but I think it'll be conceptually a little simpler. It's really the same kind of equation. The new value is k times the old value. What you can essentially do is keep iterating this equation symbolically we can replace the yn minus 1 with k times yn minus 2 to get k squared times yn minus 2. And yn minus 2 can be replaced with k times yn minus 3, which is k cubed times yn minus 3. And then yn minus 3 can be replaced by k times yn minus 4, etc. Pattern recognition here. We ultimately want this in terms of y sub 0, which would be y sub n minus n. And whatever we subtract there is ultimately the same as the power of k. So in the end, we're going to get a k to the n times y0. Because 0 is n minus n. That n up there has got to match what we subtract down there. And that's an exponential solution. N is the variable. K and y0 are fixed. K is the k that's right there. Y0 is the initial population, say. This is a function of n. It's an exponential function of n. Exponential growth when k is bigger than 1. Exponential decay when k is between 0 and 1. We saw that in lecture 2. What about the differential equation? Here is a corresponding linear differential equation. dy dt equals k times y. No subscripts anymore. Why is that linear? Well, it's essentially because I can call k times y and f of y, and that's a linear function. Here I'm sort of repeating myself. F of y equals k times y is a linear function of y. Same function as up here, actually. But now we're thinking of this as a differential equation, whereas that was a difference equation. How do you solve this? We can use separation of variables. So this is what we started talking about in lecture 2. Look at the equation, try to get all the y's on one side and all the t's on the other. K can be on either side, though it's simpler to keep it on the right. dy is something that involves y, dt is something that involves t. And even though your calculus teacher may have told you don't treat this as a fraction, we're going to pretend it's a fraction anyway. We're going to pretend we multiply both sides by dt, so it cancels on the left, and divide both sides by y, so we get a y in the bottom on the right, on the left, excuse me. We get a k dt on the right. I have separated variables, y's on one side, t's on the other. Again, dy is something that depends on y, dt is something that depends on t. These two things are called differential forms, and usually you want to integrate equations like this. I can't think of a situation where you wouldn't want to. Well, I can, but not in this class at least. And do these integrals. You know, you get k times t plus, say, c1 on the right. Here you're going to get a natural log of the absolute value of y plus c2, you could call it. Then you can subtract c2 from both sides. And say kt plus c3 on the right side. Then we can get rid of the logarithm. We want to solve for y by exponentiating. I'm being sloppy here. You should not be sloppy. I was not so sloppy in lecture 2. You should look back at what I did there. These cancel to give you the absolute value of y. We want to solve for y. Can we just get rid of the absolute value signs? It turns out you can. To get a general solution, y equals c e to the kt, where c can be any number. C is arbitrary. This represents infinitely many answers. If I have an initial condition, y of 0 equals y sub 0. Here I am using a subscript just like I did up there. Then I get a unique solution of the initial value problem. Y equals y sub 0 e to the kt. Whether a symbol is a variable or a constant is all in your head, by the way. It's all just how you're thinking about it. I'm thinking of k as constant. I'm thinking the c there is something that can change. Probably best not to call it a variable. It's just something that can change, a quantity that can change. I'm thinking of y0 as being something fixed, a constant. This represents infinitely many answers. This represents a single answer for a given y0. Okay, so separation of variables can be used to solve it. Now it's your turn. Newton's law of heating and cooling. I don't know why that's there. Erase it. Get rid of it. Oh, there we go. I guess I just had to put that down. I want you to come up with a model based on the situation I'm about to describe. A couple models, a discrete difference equation and a continuous differential equation. This is not going to be easy. And in fact, you probably need to spend a significant time on it if you're going to get it. I will give you some hints as we go. But what is the situation we're trying to model? It's going to be cooling. We're going to imagine we've got a hot cup of coffee that has been heated and placed in a cool room. Okay, I mean, if it's hot, it has been heated. Okay, I sort of repeated myself there. What is the temperature of the room? say 20 degrees Celsius, that's a fairly cold room. And the coffee's initial temperature is fairly hot, 50 degrees Celsius. What do we want to try to ultimately do? We want to be able to drink the coffee. We want it to cool down to a drinkable temperature, so we're just going to let it sit for a while. And maybe we keep it stirred. If you keep it stirred, then you don't have to worry about spatial effects so much. If you don't keep it stirred, then you do have to worry about those things. So to keep it simple, we're going to imagine we stir it consistently. After 1 minute, we're going to pretend it's down to 47. We got a thermometer in there, we're keeping track. Okay, we're a scientist or engineer, and we're sort of trying to be scientific about wondering when we can have our coffee. So we keep track of the fact after 1 minute, it's down to 47. Maybe after 2 minutes, it goes down as well. Maybe not all the way to 44, but maybe to 44.5, just to make something up. But I'm not going to say that. We are going to come up with discrete and continuous models based on some assumptions that I'll talk about here in a second, and ultimately try to find how long we need to wait until the coffee's temperature is 35 degrees Celsius, which I'm going to say is drinkably hot. Okay? This is not going to be easy. Let's talk about the assumptions, and then I'll give you some hints. We're going to assume the rate of change or actual change satisfies properties. Rate of change would be instantaneous rate of change. That would really be a derivative. That's going to be what you use for the differential equation. Actual change would be sort of a discrete change over a certain amount of time. That's going to be what we use in the discrete case for the difference equation. We're going to assume it's proportional to the difference between the current temperature and the ambient room temperature. Okay, so some hints here now. In the discrete case, we want a difference equation. And I'm really going to write a difference here at the start. I'm going to write a y sub n minus y sub n minus 1. That's the difference between, let's pretend that's the current temperature, y sub n minus 1, and that's the temperature 1 minute later, y sub n, where n can be, I guess, start with 1, 2, 3, etc. In the continuous case, and that, by the way, is an actual change. In the continuous case, we're talking about a rate of change, a derivative, a dy dt. In both cases, you assume these things are proportional to the difference between the current temperature and the ambient temperature. If we imagine in the discrete case that the current temperature is yn minus 1, we know the ambient temperature is 20, there would be the difference. These are going to be related. And in the continuous case, shall I call the current temperature yn minus 1 again? This is where it gets tricky. Just call it y. Though I'm realizing that depends on t, y minus 20. This is going to be proportional to that. This is going to be proportional to that. You're going to want to think about, is the constant of proportionality positive or negative? I will tell you that the discrete case, if you solve it by doing what I did in the previous slide, by iterating essentially, which is what you should try to do, it will get kind of complicated, and it will involve a geometric series, okay, a finite geometric series. Watch for that, okay? It's not going to be easy. But if you look up the formula for the sum of a finite geometric series, that should help you. And for the differential equation, you're going to have to use separation of variables to solve it. So now you should go ahead and work on that. And again, ideally, if you're really putting a good effort into this, it's probably going to take you about 30 minutes or something. And you may not be able to get the right answer, but keep trying. And now I'm going to go over the solution, assuming you are back from your try at this. So what's the solution? I'm going to go pretty quick, okay, because we got other things to do here in Lecture A. Solution with a discrete model. What is, first of all, the IVP? Here it is. Here's how I wrote it. Yn minus 1 is the difference in the temperature from n minus 1 to time n. It's proportional to this difference with a constant of proportionality that I'm emphasizing is negative by writing it as negative k, where k itself would be positive, so that negative k would be negative. Now, you don't have to do that. You could just write a k and in your mind pretend k itself is negative. But the key thing is the constant of proportionality itself must be negative. and the initial temperature is 50. I want to rewrite this equation by adding yn minus 1 to both sides, so that just yn is on the left side, and solve for yn by iterating. But, I mean, you can do that for an arbitrary k, but it might be nice to figure out k itself first. And that's something you can do right away. Again, you don't have to do it right away, but you can. How? Use the fact that at time 0 the temperature is 50 and at time 1 the temperature is 47. So you get negative 3, which is 47 minus 50. I didn't write the 47 and 50 in there. Must equal this thing when I plug in 50 there. So it must equal negative 30k. Divide both sides by negative 30. That means k is 1/10 or 0.1. Now we're going to use that. Again, I'm going to add yn minus 1 to both sides of this equation. That gives me this equation. And notice I'm also replacing the k with 0.1. Maybe you just had a k in there initially. Now what I'm going to do is simplify the right side. I can combine these two terms. I can distribute the minus 0.1 through the parentheses. Yn minus 1 minus 0.1 yn minus 1 is 0.9 yn minus 1. And then negative 0.1 times negative 20 is positive 2. This equaling this is another form of the difference equation. More in the form of this being a linear function of yn minus 1. So now iterate this. If yn equals this, replace the yn minus 1 with something involving yn minus 2. I guess it would be 0.9 times yn minus 2 plus 2 that goes in there. That's the next step right here. Oops. Why didn't that not work here? There we go. I replaced the yn minus 1 with 0.9 yn minus 2 plus 2. Expand this out. 0.9 times 0.9 is 0.9 squared times yn minus 2. 0.9 times 2 is, of course, 1.8, but leave it as 0.9 times 2. This is going to be our geometric series part. Notice the power here matches what I subtract there, and the power of the 0.9 here is 1 less than this power here. Keep going. Replace the yn minus 2 with something involving yn minus 3. Right there. And distribute the 0.9 squared through now to get this. Go back to red here. 0.9 cubed times yn minus 3. 0.9 squared times 2 is this. I still have this and this over here and here. Notice the pattern. Try to look at the pattern and figure it out in general, where you ultimately get to a y0, and I realized I made a typo here. Here's the answer. This should be a y0 here. 0.9 to the n times y0 plus all this is the pattern. That's a finite geometric series, and it's probably simplest to think about it from right to left. To think of this as the first term. You've learned about geometric series in Calculus 2 probably. That's the first term, sometimes called A. And the common ratio, going from right to left, is what I need to multiply each term by to get the next term. I need to multiply by 0.9 every time. R, the common ratio, is 0.9. Let's write that over here. R is 0.9. And how many terms am I adding? Look at the power of the 0.9. There's like a 0th power there because you don't see a 0.9. A first power, then a second, then a third, etc., up to an n minus first power. There are n terms here. The formula for such a sum is going to give you this, where this number right here is the A. The R shows up here and here. That's the R. And the power right there is the number of terms. Okay, so you would have probably had to look that up if you got this. So the formula simplifies a bit, and it can simplify even more. 2 divided by 0.1 is 20. Again, there's a typo here as well. This should be a y0. So the formula simplifies to this, and then I can combine the 0.9 to the n terms to get this. There's my solution based on the initial value y0. I can now plug in y0 equals 50 and get this. So here is my solution of the IVP. Now I can use it to solve for n when it's going to equal 35. Set this equal to 35. Solve for n, subtract 20 from both sides. Get this, divide both sides by 30, get this. Take a natural log of both sides and solve for n, you'll get this. About 6.58 minutes, which if we are truly thinking of this as a discrete model and n can only be a whole number, we could round up to about 7 minutes. Actually, in this situation, there's no real reason to imagine n to have to be discrete, a whole number, except that's what the difference equation assumes. Probably 6.6 minutes is something you could time it and wait for your coffee to, wait that long before you drink the coffee. The continuous model is going to end up giving us the exact same answer, amazingly enough. And here you would not want to round it to 7. Previously, if you want to round it to 7, you would want to say when's the first whole number minute when it's below 35 degrees. The continuous model is a differential equation. The model itself is this. dy dt equals, well, negative k times y minus 20. Y minus 20 is the difference between the current temperature and the room temperature. Negative k is your constant of proportionality. I hope it makes sense that the constant should be negative. Because like when it's cooling, dy dt should be negative. Y minus 20, when it's above 20 degrees, is positive. You need a negative constant of proportionality. Solve this using separation of variables. Here are the details. Divide both sides by y minus 20 and quote-unquote multiply both sides by dt. In just a minute here, I'm going to talk about a more rigorous way to think about it. You're going to get this. You got two differential forms. In this class, you want to integrate those. So we integrate both sides. Get a negative kt plus, say, c1 on the right side. Integrate this, you're going to get a natural log of the absolute value of y minus 20. The goal is to solve for y as a function of t. We could exponentiate again. The e and the log will cancel out because they're inverse functions. You'll be left with the absolute value of y minus 20. Over here, when we exponentiate and use a property of exponents, we get e to the c2 times e to the negative kt. Get rid of the absolute value signs, then add 20. And here's your general solution right here. Right, now let's just go ahead and use a c there. Is it okay to get rid of the absolute value signs? It's okay because it works. Okay, we're not being fully rigorous there. We're hand wavy. It works. There's your general solution. What about the initial value problem? Y of 0 equals 50. That allows us to solve for c. C does not equal the initial value here. It did for the exponential models, but not here. It's going to be 30 here. And that gives us a solution, a unique solution of the initial value problem when k is fixed, equal to that. Notice I'm not solving for k first here. That's typically what you want to do, is not solve for k first. We're going to use the fact that at 1 minute the temperature is down to 47 degrees to solve for k after I've got this formula. That's what I'm doing now. Plug in y equals 47, t equals 1, solve for k. K is going to be negative natural log of 0.9. You should check this work. About 0.105361, which is a positive constant. But remember, the constant of proportionality itself is negative 0.105361. Plug that in here and you've got your solution that you can use to solve for t when you set it equal to 35. And lo and behold, you get the same answer as before. Is that a coincidence? No, it's not a coincidence. The continuous and discrete models do give the same answer here. That won't always happen. In fact, in lecture 2, it depends on the problem wording, but in the problem wording in lecture 2, we did not get the same answer. Here we do. There are going to be other models where we do not get the same answer. So don't always assume you're going to get the same answer. What's really going on with separation of variables? Remember what I've talked about so far, how I've talked about that our notation is sloppy so far? That we've been writing things like y equals y of t equals something. And I said that's called abuse of notation. The y represents both a dependent variable and a function name. That's technically bad notation, but it's common notation to use in differential equations. And again, this book always uses it. Here I want to be a little bit more careful and use a different letter for the function name. And it is common to use this Greek letter right here. Kind of looks like an empty set. Some people call this phi, some people call this phi. I asked a Greek professor, is it phi or phi, and he said it was either. I've always called it phi. It seems like most mathematicians call it phi. My physics teachers seem to always call it phi. It seems like most physicists call it phi. I don't know what engineers call it. Probably phi, since they're mostly in their physics classes. That's going to be my function name. I wanted to solve this ODE, and what does that mean? By the way, ODE means ordinary differential equations. PDE means partial differential equations. You might get to PDEs at the very end of the semester. This is an ODE, it only involves an ordinary derivative. Ordinary D's, not the partial curvy D's. There's just one independent variable, t. What does it mean to solve that equation? It's the left-hand side, right-hand side stuff that I always emphasized in lectures 1 and 2. If I plug this function in on the left-hand side in place of y, that means I need to take its derivative and get that. To be a solution means I need to get the same function of t if I plug this function into the right-hand side. Replace the y with phi of t. I can do it there. I could also do it there. I should get this. That better be true if phi of t is going to be a solution, at least over some interval. For all real values of t in some interval. Now the interval could be the entire real number line, and in fact in this case it is. Or it could be some smaller interval. That's what it means. Can we solve for the phi of t? Yeah, we can separate variables, but here I'm not really separating variables in the same way as before, though it is equivalent. I'm going to divide both sides by phi of t minus 20, and that's, I'm not going to multiply both sides by dt. I'm going to even pretend this Leibniz notation is not even there. I'm going to pretend I just have a phi prime of t on the left side, and just do the division to get this. Ignore the dy dt. Just focus on phi prime of t divided by phi of t minus 20 gives me this. And I still just have a negative k on the right. If phi of t is a solution, then for all allowed values of t where at least I'm not dividing by 0, these should be equal. For all real values of t in the same interval, or maybe some smaller interval, because we want to avoid dividing by 0. Actually, there is a case where you would end up dividing by 0 here. Phi of t is the constant function 20. But let's pretend it's not. And making another assumption that this function of t is easy to integrate. It's a nice function, nice enough to integrate. We can integrate both sides with respect to t. Not with respect to y on the left, with respect to t. That I hope makes more intuitive sense as something that you should be able to do. And none of this hand-wavy stuff of pretending that's a fraction. Could write that. But wait a minute, this really ends up being the same integral. In fact, I can do a substitution on the left. I could replace the phi of t with y. And then dy dt would be phi prime of t. I could do a substitution. Actually, I'm going to do a different substitution, though related. I could let u, say, be phi of t minus 20. Then du is phi prime of t dt. And based on the substitution method, I would replace the bottom there with a u. And phi prime of t dt would get replaced by du. I'd be integrating 1 over u du. I'd get the natural log of the absolute value of u using that substitution. But then I can replace u back with phi of t minus 20. The natural log of the absolute value of u is the natural log of the absolute value of phi of t minus 20. And then it's solving for phi of t, just like we solved for y before. And we get the same answer. You might look at this and say, this is fishy too. No, it's less fishy. I mean, yes, we are making some assumptions. We're assuming we've got a solution. We're assuming this is nice to integrate. And you might wonder, does substitution, am I justifying this? Here's the ultimate justification of that, is you can differentiate this thing. And you're going to get the integrand function there. Ignore these things if you differentiate it with the chain rule. Okay? So this is a bit more rigorous, maybe not completely, but a bit more. And this goes on in reality for all separation of variable situations. You can think of it this way. It's also important to understand what's going on visually. This is done with something called the slope field. This is just going to be a very brief introduction to slope fields. Maybe so brief that you won't quite get it. Do the reading. Essentially, the differential equation can be thought of as a law that solution curves and their slopes must follow. Follow the law. Obey the law. What do I mean by that? Geometrically, what I mean is that a solution curve is going to have a slope, a rate of change, which is the slope of a tangent line, an instantaneous rate of change, at any value of t equal to negative k times the second coordinate at that time minus 20, where k is the same thing we got before. I'm pretending k is, what was it, negative natural log of 0.9, I think, 0.10 or something. And if you make a plane, a ty plane, and for any given value of y along the horizontal line, make a bunch of little line segments with slope equal to this, solutions will have to follow those little line segments like this. Notice this red curve, which is this function, the solution curve for the cooling coffee. Anytime it passes through technically the midpoint of one of these little line segments, say it's, it's close to one right here. Maybe there's one hidden right there. Close to one right here. Anytime it passes through the midpoint of one of those line segments, its rate of change, the slope of the tangent line, has to be the same as the slope of that little line segment, which is computed by plugging the y coordinate at that point into negative k times y minus 20. And you can see I've got some labels over here. For example, when y is 40 along this horizontal line at 40, these line segments have slopes plugging into the right-hand side, the y coordinate, k times 40 minus 20, which is about negative 2.1. Now, it doesn't look like their slope is about negative 2.1. It looks more like it's about negative 1. That's because the scales on these axes are different. The rate of change there, the slope truly is negative 2.1. If you plug in some other value y along some other horizontal line, like at y equals 30, and you get slopes negative k times 30 minus 20, which is about negative 1.1, you can check. And so these line segments here have slope close to negative 1. They're a little bit below 30 there. But at y equals 20, the slopes are negative k times 20 minus 20, or 0. This orange dashed line, in fact, is a solution curve, a constant function. Phi of t is always 20, which our separation of variables, that's the case where it's invalid because you'd be dividing by 0. But it is a solution. The derivative of that function is always 0. dy dt is always 0 for all t. And when you plug it in here in place of y, you get 0 for all t. It's a solution, even though, in a sense, it doesn't fit our solving, though it does fit the final formula for the solving when c is 0. Okay, I'll let you think about that. Here's our last slide for lecture A. That horizontal line has got a special name. It's called an equilibrium solution. Equilibrium solutions, horizontal lines in one dimension and points in higher dimensions. We talked about that before. Parametric curves that are constant are called equilibrium solutions, and they're really important. This constant function, when c is 0, phi of t is always 20, is a solution for this model. And it makes good sense, physical sense that it should be, right? The room is 20 degrees. If the coffee is 20 degrees to start with, it's going to stay 20 degrees. It's called an equilibrium solution. Even though equilibrium solutions like this are simple and rare, right? Most solutions are not the solution. C is anything. They are extremely important. A lot of this course is delving into reasons why, especially later in the course. They can often help us understand the nature of all solutions. In this example, the equilibrium solution attracts all the other solutions as t increases. When the solutions are above that horizontal line, they go down toward it. When they're below, they're heating up towards it. If your coffee is very cold, 2 degrees Celsius to begin with. It was in the freezer for a little while. It's going to warm up. That's a Newton's law of heating, although it's the exact same model, actually. Think about that. Solutions will increase toward 20. Because of this, equilibrium solutions that attract other solutions like this are sometimes also called sinks or attractors. Sometimes they are also described as asymptotically stable. You don't need to know those terms right away, but later on I'll be emphasizing them in the course. This is all related to the fact that the right-hand side function, the f, and its derivative, in fact, is negative k, which is negative. Okay, remember what f was. F of y was negative k times y. That was the right-hand side function for the differential equation. Its derivative is always negative k, and in particular, when you plug in 20 into that, you get negative k as well. That's negative. That's the reason why the solution attracts. I'll let you think about that as I end lecture A here. Thanks for watching.